Okay, hello, and welcome to the last and final lecture on AI in education. And the next lecture on Wednesday is going to be a Q&A session with Ariel and Zico. So again, to summarize, the last two times we covered applications of AI to learning. The first time, an application of AI to assessment, and mostly we were using the predominant AI technique we were using in machine learning, mostly actually logistic regression. This time we're actually going to talk about applications to instruction, and we're actually going to teach and mostly focus on sort of a new AI topic. It's still a part of machine learning, but it's multi-armed bandits. As a show of hands, how many of you have seen or worked with multi-armed bandits before? Okay, so some of you, but not the majority, which is nice. So for some of you, it might be a review, but not for most of you. So just to sort of look back at what we've talked about before, we've been mostly focusing on applications that have to do with predicting things. So in particular, we looked at two main applications. One was predicting performance in a learning environment. So as students are learning, can we predict how much they're learning or how well they will perform on a given task to them? And that was used to model learning, basically. And the second thing we looked at was predicting performance on a test. So if we give a student a test, can we predict how well they'll do on the test? And as we give them more items, can we get a more accurate estimation of their ability? Right? So these both have to focus on prediction, which is why machine learning is a good way of approaching these tasks. Today, we're going to focus on an application that has to do with intervention. But we have looked at a couple cases of intervention before. So does anyone remember what we've seen, where we're not just predicting how well students are going to do, but we're actually going to change what we do for the student? Does anyone remember anything we've seen in the past two lectures relating to intervention?
Adaptive testing.
Good. Yeah, computerized adaptive testing. So we saw that last time, where we decide what problems to give to students in order to maximize how much information we get about the student's ability. Right, so they were intervening to help us better assess a student's performance, right? We did see one other application, sort of, which I wouldn't expect you to get, but that was changing instruction based on a refined cognitive model. So in the first lecture, we talked about refining a cognitive model using a combination of search and machine learning. And then based on that refined cognitive model, we might realize, for example, some problems are not great, or we have to change problems to map onto different skills. So that could help us refine our instruction. That's a form of intervention where it needs a human in the loop. So we're not just using AI to refine the instruction, but the human might say, oh, based on this new cognitive model, I might want to change the problems that we give to students. So it sort of combines AI and humans. And the second application, as was mentioned, was computerized adaptive testing. Today we're going to look at choosing, sort of an ambitious thing, but choosing the best instruction we can give to a student. And this can take a number of different forms. But basically, the question we're interested in is, let's say we have a number of different instructional activities. For example, we can show the students a video. We can present them. We can give them a problem to work on. We can give them a worked example or show them an explanation. Which of these should we do? Which of these maximizes learning? Or maybe we have a bunch of different videos. Let's say we've looked all over YouTube and found a bunch of explanations for multi-armed bandits. Which of these is actually the best? And so we might give so how do we determine which of these is the best, right? And maybe I want to model my lecture based on the best YouTube video I found. So maybe I have a pool of students I can test these videos on. How do I figure out which is actually the best? So this is where multi-armed bandits are going to come in. So now just to sort of situate this in what we've already learned about, recall that we talked about, when we were talking about sort of no-regret learning, Ariel talked about the randomized weighted majority algorithm. So after each decision in this algorithm, remember, we know if each expert basically got it right or wrong, right? So we can sort of eliminate a bunch of experts, right? So can we use this in this sort of educational setting? Let's say we have a bunch of videos, and we want to present these different videos to students, and we want to determine which one is the best. Can we sort of use this randomized weighted majority algorithm, where each video is sort of an expert, right? And let's say the video either teaches something to a student 100% or not, right? To make it a 0-1 setting. Can we sort of use this algorithm in that setting? So I'm going to say we can't, because if we choose one video to present a student, we gain no information about the remaining videos, right? So it doesn't have this form where after we make a certain decision, we don't learn anything about what the other experts would have decided, right? Whether they were right or wrong. So this this motivates why we use a multi-arm bandit setting. So the difference between this and the randomized weighted majority algorithm setting is that we can only choose one arm, and I'll go into why it's called a multi-arm bandit. But an arm represents either an expert or an action, for example, that we can take. And we only know if that arm was good or bad. We know nothing about the other arms, right? So why is it called a multi-arm bandit? So I guess an old name for a slot machine is a one-arm bandit because it has an arm that you pull, and it's a bandit because it steals your money. So a multi-arm bandit is basically, imagine you have a slot machine with many arms, and different arms have different probabilities of giving you a good outcome. But the name sort of implies all outcomes are bad, at least in the slot machine setting, because it's always going to steal your money. But in other settings, hopefully there's a good arm out there, and we try to find that arm, right? I think in the traditional multi-arm bandit, if you're in a casino, is to not play. So the best arm is no arm. But in other settings, that wouldn't be the case. So in the education setting, these arms represent different actions, different learning activities or instructional activities we can give to the student. We want to find which of these activities are the best. So let me sort of formally define the setting. So we have a set of k actions denoted by this script set A. And then at each time step t, we choose an action A sub t. And then we observe a reward for that action. And that reward comes from some unknown distribution that has some unknown mean mu sub A. So, sorry, and that should be for action A. If action A has some mean mu sub A, but we don't know what this distribution is. And I should mention this is in particular the stochastic multi-arm bandit setting. There's also literature on the adversarial setting, but we're not going to talk about that today. So everything we're going to talk about today is the stochastic setting. And also in many, if you look at the literature, many times some assumptions are made about what that distribution might be. For example, maybe it's a normal distribution, but you just don't know the mean, or you don't know the mean and the standard deviation. Here we're just going to talk about it in the general setting, and then in particular cases we might say, okay, let's assume some sort of distribution over that. And then the goal, well, sort of the main goal is we want to maximize, our reward. So we want to pick the arms that maximize the reward. Another way of looking at this, as we've seen before, is we want to minimize the regret. And so the regret here, you can so the first part of the regret is sort of what the optimal outcome would be. So it would be if every time step we took the best action, right? So there has to be some best action, right? Because whatever action has the highest mean, in expectation is the best action. So if we knew what that was, we would just take that at every time step. So that's sort of the optimal outcome. But presumably we're not doing that, so then we want to compare what we're doing to the optimal outcome. And what we're doing is at every time step we're choosing action A sub t. So we want to take the expectation of the sum over all of the means of all the actions we've taken. So now if we're summing over the means of the actions, why do we need to take an expectation around that? Because the means presumably is already the expected reward of an action, right?
But every action has a different mean, right?
Yes, but I indexed it. I indexed mu by the action that we take at time t.
So shouldn't it be the reward that you got at that action at time t?
Well, if we take the expectation over that, we end up getting the mean. So yes, you could actually replace this with the reward we got at time t, but then the expectation will account for
No, assuming the distributions are independent.
Yes.
Distributions of the k arms?
Yes. Yeah, they're independent. But the thing is, the action that we take presumably depends on previous actions, right? So, I mean, our policy is changing. We're not just going to take, we could take some fixed action at every time step. But that's a pretty bad thing because we have no idea if the actions are good or bad, right? So that's why we take the expectation over the whole sum. Yeah?
So we assuming that our next step depends probabilistically on the previous steps. This is where expectation comes from.
Well, no. So the outcome of previous steps is probabilistic, right? So if let's say I took some action A1 in the first step, and I got a really high reward. And based on that, I say, OK, I'm going to take A1 again. But let's say that was a rare outcome, and usually A1 actually gives the low reward. If I gave a low reward, I might choose to do something else. So it depends on the reward, the rewards that were actually sampled. That's a good question, yeah. OK, so for the rest of this lecture, we're not actually going to look at the regret bounds for different algorithms, because the proofs are sort of involved. And so mostly I'm going to focus on just presenting a couple commonly used algorithms and just exploring them and giving some intuition behind them and seeing how they might be used in an education setting. OK, so now I'm going to give you guys a poll just to get some intuition. So let's say we have 3 actions, 1, 2, and 3, or A1, A2, and A3. And here, this histogram just shows the average reward that we've seen so far for these actions. OK, so we've so far, if we take the average of all the times we sampled A1, we got a reward of 0.9. Let's just assume this is between 0 and 1, right? And for A2, we got a reward of 0.8, and for A3, we got a reward of 0.1, right? And then below I say, suppose we took the first action 20 times, the second action 10 times, and the third action only once, right? And the order in which we took these presumably doesn't matter, right? So I'm not going to go over what order we took these. But we know that we took the first one 20 times, the second one 10 times, and the third one once. Now the question is, which action should we take next? OK, so oh, right. So the choices are, you can take action 1, action 2, action 3, or some probabilistic distribution over the actions. So the last choice gives you a lot of leeway because you're not specifying what distribution. So they could correspond to many different things. OK, a few more seconds. Just go with your best intuitive guess. There may or may not be a right answer here, so. This. OK, everyone done? Okay. All right, so let's see what people said. Oh, wow. That's pretty even distribution over the different actions, but a majority of people said some distribution over the actions. So who wants to justify any of these answers? Who's confident about their answer? Yeah.
So you don't know that whether the results you have got were a fluke or not. So it's better to take a distribution over the action as opposed to just saying, "Oh, just follow the best one you've taken so far."
OK. Does anyone want to argue for why you would take a particular action? Not, yeah.
So I don't know which action you take, but I think you should take one of them.
OK.
And,
That's the opposite. OK. Which?
and the reason being that, so each action you have some value from like taking the better action and some value from figuring out what the better action is.
OK.
But it seems, in the general case, it seems unlikely those three would all have the same like exploratory plus, expected value. So one of them is likely to be the best of whatever they are, and you should pick that one.
OK, so that's a nice argument. So you're basically highlighting the next thing I'm going to talk about, which is this exploration versus exploitation dilemma. So you can either go with what you think is best, or you can try to explore other actions to try to figure out what's best. What you were also getting at, you were saying that you don't know what's best, so let's explore more. And you were saying specifically, let's explore by doing some distribution. Because we don't know what's best, we don't want to bias it. So both of you are hinting at the same thing. I'll get to you in a second. But you're both you're giving two opposite arguments for what you want to do, which is interesting. Yeah.
But you took action 1 20 times, and you've been consistently gaining a lot.
Sorry, I missed that. Can you say?
I mean, action 1, you took it like 1
Yeah.
20 times.
20 times, yeah.
You've been consistently winning.
Yes. OK.
Why change that?
OK. So that's yeah.
I mean, okay, so yes, we saw that the first action is kind of better a lot of times, but it still could be the case that true value for the action 1 is actually a bit lower than for action 2, okay?
Okay.
So then what we can do is every time choose some distribution of the actions, and then if it will converge to something like, let's say, 1, 0, 0, then we know that the first action is the best one. So probably here, if we
Okay.
take some distribution, then probably the probability for the action number 3 will be about 0, but then about 1 and 2 maybe not, 1 and 0 maybe some, 80%, 20%, something like that. But then we can consistently take the probability distribution, and at every single point we will gain the most.
OK. Do you have a sense for what that distribution might be? Either.
Eventually it should be
Oh,
1 at,
well,
at one point.
OK, eventually, but that doesn't tell us what to do now, which is fine. I'm not.
At this point, so we should have some assumption on the probability distribution on the, on the mu ace.
Okay.
Is it a normal distribution, etc., etc. We should know some information
Yeah.
on that.
OK. Does anyone else want to see? So we're getting different opinions. Most of you are sort of have some of the same intuition, except you are saying specifically, we've done enough. Let's just go with what we know to be best. Why waste time, right? Other people are saying, no, let's explore. Some people are saying, let's explore probabilistically. Some people are saying, not probabilistically, but we don't know how. Does anyone want to give a particular action?
If you are in a casino, you can't play infinite time.
You can't.
You can't play infinite
Yeah.
time unless you have infinite money to lose.
Right. Yeah, so maybe you have a fixed horizon, so let's not waste time doing bad things, because we might, by the time we're done, we might not have the opportunity to go with what's best anymore. Okay? That's true. Does anyone want to say vote for action 2 or action 3, or like vocalize their vote? Yeah.
It's just been taken once, so
Action 3.
yeah, so you should explore action.
Yeah, okay. So that's,
It's probably a probabilistic distribution where you account for the number of trials given to that action as well as the reward you got up to that.
right. Okay. So I think most of you have sort of the right intuitions, but now let's see if we can formalize these into concrete algorithms for what we would do. Okay, so the main point that came across, and maybe I don't need to talk about this too much because it seems like most of you have gotten it, is this dilemma between exploration and exploitation. So this is sort of central to the multi-arm bandit problem, and also comes in to play in reinforcement learning. So the idea is that we want to explore, which means we want to try different actions to discover what's good or what's best. But we also want to exploit, because we don't want to waste too much time getting low rewards, right? Especially if we have a finite time horizon, or if we're discounting over future actions. We want to at some point start doing what we know to be good, right? But maybe we don't want to like also, okay, well, so what's one way of doing this? Which the way I've been talking about it was suggesting we might want to basically explore then commit, right? So we spend some amount of time exploring. In particular, this algorithm says take each action n times, and then we commit to the action that we think is best, right? So we explore all the actions the same amount, and then at that point we have an estimate over how good the actions are, and we sort of commit to the best action. And we know as n goes to infinity, we're going to converge to the best action. But obviously we don't want to do that, especially if we have a finite number of times to act, right? Okay, so there's one way of doing it. So we sort of do it this 2-phased algorithm, right? The first phase is exploration, and the second phase is exploitation. To me, this isn't very satisfying. I mean, it makes the problem not that interesting, because it's a very simple approach, but it might work. So can you think of what might be some problems with this approach?
Deciding a good end.
Okay, yeah, what n do we choose?
I mean, if n is not as large, then we can waste our time on trying the actions that seems to be bad from the beginning. So then maybe if you see that some action is very bad from like some beginning iterations, we want to switch to more exploring the other actions that seems to be better.
Right, yeah. We don't want to over-explore something we know to be bad, right? If it's consistently proven to be bad, we don't want to waste more time sampling that. Yeah?
But also, doesn't it matter the interleaving between the actions? So if I take like action 1 n times, then action 2 n times, then action 3 n times. It might be different if I take action 3 n times.
First?
Then action 2.
So you're saying doesn't the ordering matter?
Or interleave them.
So the ordering shouldn't actually matter. If we've committed to taking each action n times, right? It doesn't matter what order we take those actions in, because what actions we've taken previously don't impact the rewards of future actions. Right? Does that make sense? So the ordering could matter if we're not using this kind of strategy. But given that we're using this strategy, we can choose to do those actions in whatever order. Yeah, that's a good question. Okay, so the intuition might be that this isn't necessarily best, because we might waste some time on something we've already found out to be bad, because we've already sort of committed to sampling that action n times, right? Or conversely, maybe one action has a high variance, and n isn't sufficient to figure out what the true expectation of that is, right? Okay, so we want to try to do something more clever than this. Okay, so now we're going to go into the first algorithm. We're going to talk about 2 algorithms, 2 different approaches, which I think both came up in your answers. The first is this upper confidence bound approach. So the main idea behind this is what's called optimism in the face of uncertainty. So insofar as we're uncertain about which actions are good, let's be optimistic, right? Okay, so what that means here is these are actually the same actions, the same thing as the histogram I showed before, same 3 actions. And what we notice is that our uncertainty over action 3, as you pointed out, is very high, because we've only sampled it once, right? So these are some form of confidence bounds, which I'll go into what they are in a second. If we actually look at the confidence intervals over these, we say that, okay, action 3, we really don't know how well it does, even though it seems to be much worse than the other two actions. We've only sampled it once, right? So the idea behind this is, well, why don't we sample action 3? Because optimistically, it could have the best possible performance among all three other actions. So let's say this is, for example, a 95% confidence interval. That would mean that, let's say we knew that the confidence interval sort of captured the mean. That means that action 3 has, optimistically, it could have a higher value than any of the other two actions. Does that make sense? So let's sample action 3. Let's be optimistic about it. So why would we want to do this? Because once we sample action 3, let's say we actually find that it's bad, what would happen? Yeah, we decrease the uncertainty, and it's going to go down. If we find that it's good, if it actually is the best action, what happens?
Get a higher reward and again lower uncertainty.
Yeah. So maybe over time we'll see that it is actually better than the other two actions, and then our uncertainty shrinks, and then if we find that, for example, the confidence interval shrinks, and it's completely non-overlapping with these two, then we've sort of figured out that it is probably the best action, right? So that would be a good outcome. So that's sort of the idea behind this approach. That either way we're learning something, either we find that it actually is the best action, or that we find that it's not, and then we can not waste time with it anymore. So in particular, for example, if we after taking action 3 two more times, if we saw a reward of 0.1 each of those other 2 times, the confidence interval will get small enough that we actually think action 2 might be better now, if we're optimistic. So then we actually switch to action 2. So it only takes a couple times, if it's actually bad, before we would switch to another action, right? Then, of course, we might switch back to action 3. But over time, if it's actually bad, we're going to stop taking that action. That's the general idea. That make sense? OK, so now let's formalize this. So this is the UCB1 algorithm. There's many sort of different instantiations of this. This is sort of the simplest, and I think the first one that was proposed, which is you take each action once to begin with. OK, so you do an initial exploration, so sort of like the explore and commit strategy, but you only do it once for each action. And then afterwards, you're going to take the action according to this equation. So you're going to take the argmax, the action that sort of maximizes this quantity. What is this first part here? Yeah, so the empirical average reward so far, right? And then the second part is sort of our confidence interval term, right? So it's the square root of 2 times the natural logarithm of the total number of actions we've taken so far. So as we take more actions, this quantity is going to decrease, because our confidence interval should decrease, divided by the number of times we've taken this particular action, right? So this is the confidence intervals that I plotted here, OK? That makes sense? And you can derive this from sort of like from a Chernoff-Hufting bound.
Why decreases the? So if you take actions and increases, and then the logarithm increases, and that thing increases. Can you repeat?
Yeah. Oh, yeah. I said it wrong. Yeah. So sorry. As the number of actions, that term does increase. But I was thinking of that. As the number of times you pull a certain arm increases, then the denominator would increase, so this term decreases. Sorry, I said it wrong.
So n is what?
N is the total number of actions we've taken so far. So the total number of time steps.
So it still increases.
Yeah, it increases very slowly though,
Oh.
because it's a logarithm.
And then j increases faster. Okay.
Yeah, and j is exponentially faster.
What's the reasoning behind getting this?
Why this particular?
Yeah, you said
Version.
you use the Chernoff-Hufting bound to
Yeah.
but
So it's basically it's a confidence. It basically represents some confidence interval, and in particular, I think it's without making more assumptions about the distribution. So you can get better confidence intervals if you assume, for example, the rewards come from a Gaussian distribution. So you're basically use a concentration inequality, and this.
This is the binomial.
No, I think the only assumption this makes is the rewards between 0 and 1. So this particular algorithm assumes the rewards between 0 and 1, but doesn't make any more distributions about the distribution for each action. Which is a good point, because that means this confidence interval is very loose in practice, right? And actually, if we go back to these plots, what do we notice about these?
all bigger than one.
Yeah, so the upper bounds are all bigger than 1. Actually, we know that they're not. So a true confidence interval would cap it at 1, right? But the algorithm, I think, still says you go with, I mean, it doesn't say to cap it at 1. So these aren't actually valid. I mean, they are valid confidence intervals, but they're looser than we even know to be true using our knowledge that the rewards are between 0 and 1. So that shows that it's quite loose. And only once we've sampled actions enough times, so even more than 20 times, do we actually get confidence interval where the upper bound is lower than 1. Okay, any more questions about this?
Is that confidence interval of what percent? I mean,
Oh, what percent
Yes.
confidence interval? It's not. So I think it's not. To look at derivation, it uses some. It's not. I don't know if it corresponds to an exact percent, or that it's derived using some other quantities. So it might correspond to a percentage, but that might depend on other terms. Actually, I'm not sure. Yeah, that's a good point, because it doesn't have like a delta term in there. Normally, like when you derive a confidence interval, you're gonna have like a delta term, a high probability term, but then you do some other manipulations to derive this particular form. So in practice, actually, what people do, I think, you'd actually multiply this term by some constant, so you might scale it down, and it might actually do empirically better. This form is derived in order to get better regret bounds. And sort of the asymptotic regret here is logarithmic in terms of the number of time steps. So asymptotically, it's 0 regret. Yeah. OK, so now I'm going to go into the second approach. Oops. Yeah, the second approach, which is Thompson sampling. So first, are there any more questions about this algorithm? So the main takeaway, I think, is just sort of the general intuition behind how this algorithm works. Right? And then there's many different, you can play around with different concentration inequalities to write different forms of these algorithms. Mostly it's done to make the regret analysis work. But the general idea of sort of being optimistic with respect to a confidence interval is what works, and that idea is what's useful in practice. Not necessarily like the exact theoretical algorithm. Okay. So now I'm going to move on to the second approach, which is Thompson sampling. So this is a Bayesian algorithm, and this one, for those of you who said we should do a probability distribution of our algorithms, you could be right. You could defend that answer. So actually, just to go back to the poll, so the correct answer, if you're using the UCB algorithm, would have been to take the sample action 3, right? For those of you who thought that's the case. But there is no real correct answer. Maybe you can find another algorithm that justifies taking action 1 or 2. But in this case, for Thompson sampling, the correct answer is to do a probability distribution. Now the question is, what probability distribution? So our algorithm says we choose actions according to the probability that we think it's the best action, right? So this is a Bayesian setting. So that means for each action, we have sort of a probability distribution over how good we think that action sort of is. And then we choose the action according to the probability that we think it's the best. To make this more concrete, we're going to take action A sub j with this probability. Maybe I should write this out. OK. Well, so this sort of looks annoying, but it's actually not. It looks more complicated than what it is. So this first term, it's an indicator function. It's an indicator function that for the expectation of this action being equal to the expectation of the best action. So basically, it's an indicator function saying that given some parameter theta, right? So our probability distributions are now going to be parameterized by some theta. Given that theta, is action A sub j the best action under theta, right? So either is or it isn't, right? That makes sense. So all this is saying is it's a 1 or a 0 depending on whether AJ is the best action given theta, and then we integrate this with respect to the probability distribution over theta given our data. Does that make sense?
What's the theta again?
Theta? Theta is some parameter for the distribution.
What the distribution of what?
So good question. For the distribution of the rewards. So the rewards, yeah, let me write this. So we assume the reward for action J, let's say, let me write this as, yeah. The I time step, and it doesn't matter what time step it is. It's going to be sampled from some distribution P that's indexed by some theta, right? That makes sense? So then we're going to have a problem. So because it's a Bayesian setting, we're going to have a probability distribution over theta given our data, right? So what is our data in this case? What data do we have from the past?
Sample so far.
Yeah, so basically rewards, right? So this is sort of the set of rewards, I guess. Basically, the set of, sorry, R sub j i. I mean, you have the rewards for all the actions, but it's only going to depend on the rewards for action j. So maybe I should say this is the data, the set of samples for action j, right? Because those are the only ones that it depends on. For if we're looking at this, yeah. Let me just say probability distribution for action j only depends on the samples we've collected for action j. Does that make sense? Okay, I'm going to make this more concrete in a second. But how do we actually compute this? This seems like a sort of nasty thing to try to compute. Does anybody have any guess for how we're going to actually do this? Not necessarily how do we compute it, but how are we going to actually implement this algorithm? It's in the name of the algorithm. Yeah, so we're going to sample. We're not going to actually compute this integral. What we're going to do is we can just sample a theta according to our posterior distribution over theta, given the data. That rhymes. And then we take the action that's sort of optimal with respect to that theta, right? Because then we can, yeah, right, sorry. Then we can compute which action, given a particular theta, we can compute which action is actually optimal. Because theta basically specifies what the probability distributions are for each action. Does that make sense? So then we know, assuming that theta is correct, we know exactly which action is optimal, so we just sample that action. Okay, so now let me give a concrete sort of instantiation of this where we're using a beta distribution prior. So we're going to suppose each action gives rewards according to a Bernoulli distribution. So now I'm going to assume a particular distribution. So each action either gives a 0 or 1 reward, but we don't know with what probability we get a reward of 1, right? So we want to find the action that has the highest probability of giving us a reward of 1. So we're going to assume that action A sub j gives a reward of 1 with probability P sub j. Okay? And then we're going to use a conjugate prior, in particular a beta distribution. So this prior is, so the probability that, so actually I should specify here, theta is going to be equal to basically just the probability for each of the k actions, right? Because for each action, P sub I, for action A sub I, P sub I tells us the distribution of the action. It's just a simple Bernoulli distribution, right? So theta is just basically the set of those probabilities. Sorry, the vector of those probabilities. So in particular, our the probability of P sub j is going to depend on two hyperparameters, alpha and beta, and it's going to be proportional to P sub j to the alpha times 1 minus P sub j to the beta, and then there's some divided by some normalization constant, right? So what's the probability of our theta now? First of all, what are all the hyperparameters we have? We're going to actually have hyperparameters for each P sub j, but we're going to assume it's the same. So I'm going to assume for all of them, it's going to be just some fixed alpha and beta. So the probability of a particular theta, does anyone know what it is? So we have for each P we have this quantity, right? Okay. So then we multiply these all out. So we just write this probability of P sub I over all I. That make sense? Theta is just a vector of all the probabilities. Okay, so why do we use this prior? Well, I've already said it's a conjugate prior. So after we take some action A sub j, if we see a reward R sub j, so remember R sub j is either 0 or 1, what is our posterior going to be? It's going to be this quantity here. So here we have, so basically it decomposes into the prior times the probability of having sampled R sub j given the P sub j is the true probability, right? So they're just applying Bayes' rule. Okay, and then what is the probability of sampling R sub j given P sub j? It just follows a Bernoulli distribution. So we can say it's P. So if R sub j is 1, it's P sub j, right? And if r sub j is 0, it's 1 minus p sub j. Right? And we can write that as p sub j to r sub j times 1 minus p sub j to 1 minus r sub j. Because either one of them is going to be 1 or 0. And then that'll basically pick out whether we want p sub j or 1 minus p sub j. Right? So if we simplify this, we just get that it's equal to p sub j to alpha plus r sub j times 1 minus p sub j to beta plus 1 minus r sub j. Okay? So that's why it's a conjugate prior. Because then we end up with a beta distribution with just the parameters alpha plus r sub j and beta plus 1 minus r sub j. Okay? Now in particular, once we do this many times, after any action, the posterior distribution is going to be as follows. It's going to be p sub j to alpha plus s sub j, which is the number of successes for action j. Right? So each time I sample action j, you can think of we either have a success or a failure. So basically, we just take alpha plus the number of successes times 1 minus p sub j to beta plus the number of failures. Right? So this specifies what the distribution is for p sub j given all of the actions we've seen so far. All of the rewards we've seen so far. Okay, any questions about this? Okay. Okay, so what is the algorithm now? So for Thompson sampling, it's very simple. All we do is we sample each of these p's with the following probability distribution. So with the distribution p sub j to alpha plus s sub j times 1 minus, proportional to p sub j to alpha plus s sub j times 1 minus p sub j to beta plus f sub j. Right? So we sample p sub j from this distribution for each of the k arms. And then we simply take the max over all the arms, where the max is just which one has the higher p. So basically, we sample a bunch of probabilities, and we basically choose the arm that had the highest probability sampled. And then we update our posterior distribution. Any questions about that? OK, just to see if this makes any sense, I'm going to ask a poll. OK, so how can we increase exploration? Remember, we want to trade off between exploration and exploitation. I haven't talked about how Thompson sampling does that directly. So how can we increase exploration using Thompson sampling when we have this beta prior? So can we increase it by choosing a large alpha, choosing a large beta, choosing an equally large alpha or beta, or you have no idea? OK, and I'll put up the equation again, or the algorithm. So we can specify what alpha and beta are in the prior. So the question is, what alpha and beta should we pick, or relatively, to increase the amount of exploration in our algorithm? Yes? Yeah. Let me see. Yeah, I could do it. Okay, it should be up, but you have to type the URL. Okay, everyone done? Okay, let's see. So, okay, I guess the plurality was to choose an equally large alpha and beta. And then people thought, and then the next best was choose a larger beta, and then choose a large alpha. So anyone want to advocate for their answer? Yeah.
Large alphas and betas, the S and Fs, the successes and failures you get have less of an impact on like your initial configuration of what you think the probability should be.
Okay.
And so you're less influenced by like results that come in, so you're more likely to explore
Okay.
the probabilities.
Okay, so he's saying if alpha and beta are both large, then basically future rewards have less of an impact over your basically what happens. Over what action you choose, because it impacts the probability less. So if alpha and beta are just as they go to infinity, basically any future observations we see don't impact the distribution, and we're going to equally sample all actions. Okay. Does anyone want to advocate for choosing a large alpha or a large beta? So what happens if you just choose a large alpha? Yeah.
If you choose alpha and beta equal but very large, because you're choosing like proportionally to this, then you have to normalize, and it will just those alpha and betas just will cancel out. So then the future impact of S, J, and Fj will be the same. I mean, if alpha equals beta, no matter alpha and beta are large or small, the impact of Sj and Fj will be the same. No? Because you normalize that.
Okay, so the question, okay, so let's say alpha is like,
No, it's for the,
yeah.
for the previous explanation. It's not the
Yeah,
explanation.
no, I understand.
Yeah.
So let's say alpha and beta are both 100,
Yeah.
and now we get one success, right? So now we have alpha to the 101 and beta to 100 for this
But
action.
then you have to divide to the sum of all of those. And in this fraction, we will cancel out pj to the alpha and 1 minus pj to the beta, like to the 100. No?
You're not canceling out. So we have a set of actions, right?
No. No, wait.
So the impact it has, if I understand correctly, we have, okay, let's say we just have two actions, right? And let's say alpha and beta are very large. And now for one action, we get a success. So now we have alpha to the 100 times beta, alpha to the 101, let's say, and beta to the 100. For the other action, we have alpha to the 100, alpha plus 100 and beta plus, p to the 101 times 1 minus p to the 100. And for the other one, we have p to the 100 times 1 minus p to the 100. And so those two are very similar. And then when you normalize, you divide by the sum of those two. So the two quantities are just going to be very similar, even though you had one more success for one of them. Does that make sense? So what happens if we just increase alpha?
We just getting a lot more probability of being that action to be a good action. I mean,
But for all actions, right?
if Sj is, yeah, like for all of them. Yeah.
All actions seem good.
Yeah, all actions seems good.
Okay, so we're sort of optimistic for all actions, right? And then if we get more successes, it's going to have not that much impact on the action. But if we get failures, it's going to have sort of more of an impact. So it's different forms of exploration, right? You can think of, depending on what you want to do. So okay, if we increase, so it's not as concrete, I think.
I mean, so if we want to explore more, we probably want alpha and beta to be 0, no?
No, that's actually not what we want, right? Because okay, that's a good point. So if alpha and beta are both 0, then everything's going to depend on our future, what we find. So if we get,
And that's why we explore more, because we know kind of nice. Like if you increase alpha and beta, it kind of saying, oh, well, like we know something.
yes,
For example,
but alpha and beta are the same for all actions, right? So we're saying we know a lot about all the actions, and what we know is that they're all about the same.
Yes.
And that doesn't matter which one is larger.
So that's why we decrease the exploration, because we already know some amount of information. No, maybe not. I don't know. It's just kind of the intuition. If we already know some information, that's why we really explore less. But then if we know nothing, we will explore more.
No, so we're saying we know a lot, but we know that we think all the actions are the same.
Simultaneously, yeah.
Yeah. So it's going to take a lot of more knowledge to think that one action's better. So we're going to keep exploring. We're going to keep sampling randomly until we get a lot of knowledge about one action being much better. That make sense? So I guess this wasn't a very good question because it actually, which one we increase just sort of increases all the actions we are going to think are equally good. But in one case, we're going to think they're all really great. In one case, we're going to think they're all really bad. And in one case, we're going to think they're all medium, I guess, right? But increasing each of them is going to increase our amount of exploration. So how do we increase the amount of exploitation? We decrease alpha and beta. So if alpha and beta are very small, if they're 0 or 1, then that's going to give us very little exploration, right? Okay, you still have a question?
No.
So basically, we can increase. So if we pretend we have more prior knowledge about all the actions, but we pretend we have the same knowledge about all the actions, then it's going to increase the amount of exploration. It's going to take longer before we sort of converge to one action being better than the others. Okay. Any questions about Thompson sampling? Okay. So now I'm going to give one concrete example. I haven't talked about education in a while. I'm going to give one concrete example of how this has been used in sort of an educational setting. And so this is a paper from last year. So it's called Axis: Generating Explanations at Scale with Learner Sourcing and Machine Learning. Okay, what's learner sourcing? So it's this new idea. It's a form of crowdsourcing where we're sort of collecting, we're getting knowledge from the learners. So this example comes from, when we have these large online courses or MOOCs. We have lots of learners, we have lots of students. Can we use those students to sort of improve our education? So this idea is going to connect the fact that we have lots of students, and presumably we can, gain knowledge from those students, and then we're going to combine it with multi-armed bandits in some way. How are we going to do that? So first, this is just an example of a problem. So this is sort of this wasn't actually deployed in a real course. This was done on Amazon Mechanical Turk, so it was done on crowd workers. Those are our learners here. But it sort of still illustrates how this could have been used in a course. And hopefully it will start gaining traction. So this is just an example of a problem that they tested. These are sort of simple math problems. So here, the problem is a probability question. And then they're asking the crowd workers to enter the answer to the question. And then what they do is, once they enter the answer, for some crowd workers, they're going to give them an explanation. And this explanation is going to be taken from other crowd workers. Okay? So either, when I do this task, either I'm asked to give an explanation for my answer, or I'm going to be presented an explanation from another worker. So here, this is the explanation presented from the worker. And then I'm going to be asked, how helpful is this explanation? Okay? So as we keep doing this, if we keep collecting explanations from a bunch of workers or a bunch of students, we're going to increase the number of explanations we have. And now we sort of want to filter and say, OK, which of these explanations are actually useful? Okay? So what is our metric for whether an explanation is useful? In this case, what they used is whether other workers or other students thought they were useful. So if I rate this explanation as being perfect, 10 out of 10, then the system is going to think, OK, that's one sample. One person thought this explanation was great, right? So that's sort of the reward that we obtain. Yeah?
But is this for correct answers or even wrong answers?
Good question. It could potentially be a wrong answer. Actually, I think they filtered on. That's a good question. I can't remember if they filtered on only people who gave right answers or wrong answers. So in some cases, you might not know what the right answer is, so that makes it more tricky. If you do, then you can only filter on right explanations. There is actually some reason to believe maybe that wrong explanations could be useful, but you don't want to tell the person that it's a right explanation in that case. You want to say, you might want to ask them, here's an explanation someone generated. Is this correct or not? Maybe identify the flaws if it's wrong. But if you tell them it's right, that could be bad for learning because you're giving them incorrect.
Characterizing right and wrong explanations, we're characterizing helpful and unhelpful.
Right. Yeah. So I believe, I think only explanations were given that were correct, at least at some level, that we didn't have incorrect information. But the other point that I think you might be getting at is that we're not characterizing whether an explanation actually is helpful, right? If it leads to the workers doing better later on, right? right? So ideally, that's what we would care about. We care about if we give an explanation to someone, down the line, are they going to get these problems are they more likely to get these problems correct or incorrect, right? And so that should be a reward signal. What's the problem with that reward signal? I mean, it's not really a problem, but there's sort of a delay between the time that we give the explanation and the time that we can measure the reward, right? So if in particular, if we're giving a series of explanations and then we're measuring their performance, then we don't know which explanations were helpful or unhelpful, right? Because we don't know if the first explanation was helpful and that's why the student did well, or the last one was helpful. And it could take a while before we actually get a reward signal. So it makes it less fast in order to intervene. So I think the one reason to do this, where we sort of ask the person, is it helpful or not, is that we get a quick reward, which is what's assumed in a multi-arm bandit, that we get a reward immediately after taking the action. But that's one problem with sort of doing this in educational settings, is that good reward signals might take a long time to measure. For example, let's say we're doing some sort of intervention where we want to measure, how that's affecting like high school graduation rates. It's going to take a long time before we actually measure that. So using a multi-arm bandit in that setting might not be the best thing, or it might not be the easiest, right? So the assumption here is that users have a good sense of whether an explanation is helpful or not to them. That could be incorrect though, and that could be partially why it's noisy, right? Or distribution, like, so maybe let's say the true mean of this explanation is 8, but because users are bad, so some people think it's not helpful, some people think it is helpful, so the mean is actually noisy. So there's actually two levels of noise in some sense. One is that the explanation might have varying levels of helpfulness to different people, right? So there's a distribution over to that, and maybe the mean is high or low, but there's some distribution. A second is that there's some noise because people don't know how helpful an explanation actually is to them, which is sort of I guess that level of noise is not typically modeled in multi-arm bandit. We're going to assume that's sort of not there. Okay, so what they did is that once they've collected these explanations, so there's this additional problem of you want to collect explanations as well as showing explanations. So from some workers, you want to collect explanations, and for some workers, you want to show the best explanation. And so that's not a multi-arm bandit problem. I don't know how they sort of chose whether to collect an explanation for someone or show it. But once they've collected enough explanations, at that point, you want to sort of figure out which one's the best. So that's when it becomes sort of a multi-arm bandit problem. So let's say we have 100 explanations. How do you figure out which one's the best? So what they did is they used Thompson sampling. So and in particular, they used the beta distribution that I just mentioned. They actually used the beta distribution. I don't have it here, but with alpha equals 19 and beta equals 1. So what this actually corresponds to is, remember, we're assuming a 0 or 1 signal here, right? But the reward that we actually obtain is between 1 and 10. So what they're going to say is they're going to say each user actually gives us 10 different rewards. So this, again, is sort of different from what the standard assumption is multi-arm bandit, which is you get 1 reward signal. They're going to say we're going to get 10 different reward signals. And basically, if they give them an 8, you're going to get 8 successes and 2 failures, right? So the number of successes you get is the rating that they gave, and the number of failures is 10 minus the rating they gave. Okay? So what is this an alpha of 19 correspond to, and a beta of 1?
We already have 19 positive rewards and 1 negative.
Yeah, but what would that correspond to if that was actually generated from, let's say, users? How could we have gotten 19 positive and 1 negative?
2 users answered 10 and 9 and 1.
Yeah, 10 and 9, right? So one user, we're assuming the prior sort of that for each arm, one user, for each action, one user give it a 10 and one user give it a 9 in the past. So that's just what they chose. So there's always this question of how do you choose your alpha and beta? Again, it's sort of saying that
statistically or something like that, they
no,
just choose it.
They just choose it, yeah. But the idea is that unless you have prior knowledge about some actions being better, the thing you definitely want to do is you want to say that all actions have the same, alpha and beta, or all actions have the same prior distribution, unless you have some prior knowledge that some explanations are better. Okay, so these are some of the results they found. So what they actually did is they used this multi-arm bandit for like 150 users, doing a series of problems, and then they took the policy that was generated at the end of that, and they tested it on like 400 or 500 new users to see how does it compare to an expert instructor's explanation, as well as a random policy. So policy that just randomly gives different explanations. Oh, sorry, actually, not a random policy. What they did, one thing I didn't mention, they actually filtered out bad explanations using some deterministic rule, like if the explanation is too short. So again, this is again up to the user how they want to define this. But they said some explanations we have some prior knowledge that they're just bad, so we're gonna even disregard them. We're not even put them in the multi-arm bandit. So what they did is they compared to these discarded explanations to say, okay, does our algorithm do better than these discarded explanations? What they should have, I think they should have compared to a random policy to see if using a multi-arm bandit actually is better than some sort of simpler, randomly choosing actions. I guess they didn't actually do that. So this isn't maybe it's not the most interesting comparison. So basically, if we look at this first thing, for the first row here, it's saying how did these new users, how did they rate the helpfulness of explanations that were discarded, explanations that we thought were actually bad, versus explanations that this axis. So after 75 users have been in the system, the explanation that we would give to the 75th. The posterior distribution after the 75th user, and then the posterior distribution after the, I think this is incorrect, after the final user, the 150th user, right? So it's basically taking two snapshots of the multi-arm bandit policy, one after seeing 75 users and one after seeing 150 users, and it's comparing those to see if it improves over time. And then finally they compare it to an expert explanation for the problems. And I guess what they're saying is that the policy does better than these sort of explanations that were discarded, so the ones they thought were bad, and it's approaching sort of an expert instructor's explanations. What's maybe more informative is how well it actually helps the students solve problems, or these crowd workers solve problems, right? So the perceived helpfulness is sort of increasing, but how does it actually affect their problem-solving ability? So that's what's shown in this third row. And again, here it's actually, I don't think it's significant, but it's saying that the axis policy is actually, like the problems, the explanations that it's presenting are on average actually better than the instructional designer's explanations, and they're much better than these bad explanations. So it's actually, the effect is actually even stronger when you look at how well it impacts the student's ability to solve problems than how useful they think the explanations are. So these are just some results. There's more. I think it's an interesting use case for to sort of collect these explanations from a crowd and then trying to figure out which one's best, right? And I think there's a lot of ongoing work now trying to go in these directions. For example, getting users to create videos, like YouTube videos, explaining a topic, finding out which of these YouTube videos is actually most informative. Or we can just scrape the web, come up with a bunch of YouTube videos that explain different topics and coming up with the most informative. Because currently, there's many videos if you're trying to look up, an explanation to a topic, like in Khan Academy or different websites. How do you actually know which is the most effective? So I think these sort of multi-arm bandits can be used to determine what's the most effective. Now, typically, in sort of the standard approach in these settings, when we're not using a multi-arm bandit, it's what's called A/B testing, right? So let's say we have two different alternatives, and we want to test which of these is the best. So the way we typically do is we just run an experiment where we test both of the alternatives on a bunch of people, and then we basically compare sort of how good they do on average, and we just go with the average. So just to check your understanding, what does multi-arm bandits give us on top of this? So we could sort of run an A, B, C, D, E, F, G test, right? Where we compare a bunch of different alternatives, on a bunch of users, and then just see which one's better on average. So why use a multi-arm bandit? Why is that actually useful? What does it give us beyond just doing a simple experiment? You can compute those in an experiment, right? Confidence intervals. In fact, the experiment's much cleaner, right? Because we have the same number of samples from for each condition, right? It's very easy to compute confidence intervals.
Sort of the same problem with n times testing, right?
With what?
When you
you're testing anything, then you're discarding sort of the information that you're getting in between.
Discarding what information?
Not discarding, but basically not taking into account the information adaptively that you're getting. So if some explanation is bad, then you're just still doing the test.
Yeah. So you're saying that as we're doing a test, if we realize it's bad, then why keep going with that, right? So that's sort of the same thing we had with the explore then commit strategy, right? In fact, that was exactly running an experiment. For each arm, we're basically treating it as a condition and experiment. We collect n samples from each, and then we figure out which one's best. It's actually a very good point. So that's exactly what we do if we run an experiment. So what's a disadvantage is that we might be oversampling for something that we know to be bad, for example. So what multi-arm bandits effectively do, the only advantage is how many samples do we need in order to figure something out. So they basically help with this sort of sample efficiency problem. It tries to minimize the number of samples you need in order to get like high reward, basically, right? Because you could just run an experiment, but you might be wasting, if you're doing it on actual students, you might be getting more bad outcomes for students. So you want to minimize the number of bad outcomes you're actually getting for students. Okay? So there have been there have been other papers, and I can give you pointers to other cases of multi-arm bandits using, for example, the UCB algorithm we talked about in different settings, different educational settings. For example, like choosing the parameters, like design parameters in an educational game to make the game most engaging so students stay in the system the longest. And I'm still not clear actually how, this hasn't really impacted, I think, education. Like, I don't know if these interventions are being used by industry, for example. They might be, but there have been a number of research papers. I don't know to what extent it's actually impacted like true, interventions used in actual educational settings beyond research papers, and beyond like Mechanical Turk studies in particular. So it seems like a nice idea, and it seems like something that could help. But it's sort of a very sort of new idea in the educational community to actually be using these. And actually, multi-arm bandits in general is a very growing body of topics. So if you're interested in this, like the literature on this is, there's a growing interest in this area. So a lot of people are doing more research. So actually, one question I have is what's sort of missing here? So the question, what we're looking for here is we're trying to say what's the best educational, instructional activity to give to students, right? But is that really the right question to be asking? What's sort of missing from that question in some sense? Sort of an open question, but. So is there one instructional activity that's best for all students, for example? Maybe, maybe not, right? So we might want to sort of personalize. There's a lot of talk about personalization. So how do we sort of find the best instructional activity for each individual student, right? So in that case, maybe we'd want to do like a multi-arm bandit for each student individually. That might not make a lot of sense because we might not want to give a bunch of videos to the same student and see how well they do, right? Each one does. That might be a waste of time, and that student might get annoyed that we're giving a bunch of videos for the same topic, right? But there's different ways to approach this. So one way is contextual bandits. So I'm just going to briefly talk about this, just so you get some familiar with this. So one algorithm, for example. So contextual bandits is the case where we assume there's some context. So when we see a new user, the new user comes with some context, and we want to give the best action given that context. So now we're not just assuming that there's one universally good action. We're assuming that for each context, there might be a different optimal action, right? So for example, in the educational setting, maybe we have some parameters over different users. For example, what the prior knowledge is. So maybe we've used some of the techniques we talked about in the past. For example, using item response theory to sort of measure what their ability is, or maybe what their ability on different skills are. So we have this information as a context for each user. And now we want to say, okay, what activity should we give to the user based on that context? So I think contextual bandits might have more promise in the educational setting. It might be more interesting, but I don't think they've been used that much yet. So I'm just going to go over a couple ways to extend the algorithms we've already seen for this contextual bandit setting. So the first algorithm is LinUCB. So it's an extension of the UCB, or upper confidence bound algorithm. So what it says is that we obtain some context. This says x sub ta. So this means that the context is actually dependent on. So at each time point, we get a different context depending on which student we see. I actually should have just written x sub t. This is actually saying the context also depends on the action. So there's some interaction between the time step and the action, which is actually what the LinUCB algorithm says. But I think I just wanted to simplify this, but I wrote the wrong notation here. I wanted to simplify it. Let's just say that the context only depends on the time step. So we just have some context variables for a user. And then, so this context is going to be some vector of different parameters for the user, different parameters for the student. And then we're just going to assume a linear payoff function. So we're going to assume that the mean value, the mean reward for an action, given the context, is sort of the dot product between the context and a set of features for that action. Right? So we're assuming for each context variable, we have a feature, we have a coefficient for that action. And then we just take the dot product of those coefficients with the context variables, and that gives us the mean reward for that action. Right? So we're assuming this linear payoff function. This is an assumption, but might hold well in practice. So how can we now use this? How can we apply the UCB algorithm assuming this assumption? So just sort of like a very high level idea is, so we solve for basically the theta, the parameters, using some form of linear regression, right? Because it's a linear problem. And then we build confidence intervals over the mean, and then we can apply UCB in the same way using those confidence intervals. Right? So I'm glossing over all the details of this, just to give you that sort of like the high level of how you would incorporate this context. Okay, are there any questions about this? Okay, and then last thing to look at is how would we modify Thompson sampling if we're given context? There it's actually even more simple. So we assume we're given some context x, and all we do is we're going to take the action aj with probability. We have the same expression as before, except that we're just going to condition over the context. So we're going to assume our probability distribution of rewards is just conditioned over the context. Of course, again, it's going to depend on what distribution assumptions we're making, just as Thompson sampling did before. But now we're just saying that the distributions are going to incorporate that there's some context, and we're conditioning with respect to that context. But the same algorithm structure applies. Okay? Any questions about this?
Why context is not inside our data? I mean, why theta does not depend on the context?
It does.
Oh, it does. So
Very
X
good question.
is inside data.
Yes. Sorry, I should have mentioned that. That's why I made data red. So the data now concatenates the context as well as the rewards. So the data depends on both. Yeah, sorry. I specifically made that red to point that out. But okay, so this doesn't really tell you what distributional assumptions to make given the context, but that's up to the particular problem and what priors you want to assume. Okay, so that's one modification. Just very briefly, what's another way we can sort of personalize instruction for students? So one way is to assume that there's some context. So another way is to assume there's some context, but that context might change over time, right? And that's where adaptivity comes in. Another hot word. Personalization, adaptivity. You're going to hear these a lot. It means different things to different people, but they're hot topics, whatever they mean in the education world, and other contexts as well. So the idea is that the user has some context or some state, and that state changes over time. And that's where reinforcement learning comes in. So I'm not going to talk about this. I'm just going to mention that reinforcement learning is basically an extension of multi-armed bandits to this situation where there's some state, and that state is changing over time. So in this educational setting, we might think that state sort of parameterizes the student's prior knowledge, and that knowledge is changing as we're intervening. So as we teach them new things, the student's learning is changing, and then we want to decide what to teach to the student based on their updated state. So that's another way to do interventions in educational settings. And there we might want to decide what's best at each time step. So that's similar to the computerized adaptive testing. But unlike the computerized adaptive testing, we don't want to be adaptive in trying to maximize our information. We want to be adaptive in trying to maximize the student's learning, which is in some ways a much more difficult problem. Okay, and that's all I have for today. Are there any questions about all three of the lectures, the past 3 lectures on education? No? Okay. Thank you very much. So remember, Wednesday there's going to be a Q&A session, and that's the last class for this course.